All right, let's get into this. Inside the walls of pretty much every modern building, our offices, factories, even our homes, there's this secret battle going on. Think of it like a detective story for electricians. The clues are flickering lights and wires that are way too hot, and the culprit, well, it's this invisible saboteur that's quietly trying to wreck our power grid from the inside out.
So what is this invisible threat? I mean, picture this. You're managing a building. You've got brand new computers failing left and right, circuit breakers tripping when they shouldn't be, and your electricians are telling you that the neutral wires, the ones that are supposed to be safe, are getting dangerously hot. But here's the kicker. Everything's wired up perfectly. It's a total mystery, and it's costing a ton of money, causing downtime, and honestly creating a serious fire risk.
The key to solving this mystery is right here on this slide. So on the left, you see that perfect, smooth curve? That's a pure sine wave. That's the clean, healthy electricity our entire grid was designed for. But on the right, well, that's what our power actually looks like a lot of the time now. It's this jagged, chaotic mess. This is what we call electrical pollution, and it's being created by the very devices we depend on every single day.
Now this pollution, it has a name, harmonics. They're basically these unwanted higher frequency currents that are piggybacking on our main power supply, and they just create chaos. And the really wild part is where they come from.
See, it's not some giant, rumbling industrial machine causing the problem. It's all the small stuff, and it's everywhere. We're talking about the power supplies inside our computers, the drivers in our LED lights, our TVs, our printers, every single one of these devices, these nonlinear loads. They take that beautiful, clean sine wave, chop it all up, and then spit this electrical noise right back into the building's wiring. But here's the thing, not all harmonics are created equal. There's one particular type that is, without a doubt, the main villain in our story. They're called Triplen harmonics, and in our modern three-phase power systems, they are uniquely dangerous. Okay, so here's what makes these things so incredibly sneaky. In any big building's power system, you usually have 3 separate power lines, right? We call them phases. And the whole system is designed so that their currents balance each other out and cancel out in a shared return wire, which we call the neutral. It's a really elegant, balanced design. But Triplen harmonics just throw a giant wrench into the whole thing. Because of their specific frequency, they're all in phase, which just means they don't cancel each other out. They all line up perfectly.
And this shows the problem perfectly. Instead of canceling out and leaving that neutral wire with basically zero current, these Triplen harmonic currents from all 3 phases just stack. They pile on top of each other. They add up in the one wire that is supposed to be carrying almost no current at all.
And this adding effect is genuinely terrifying. The current in that neutral wire, which by the way, is usually the same size as the main wires, can get overloaded by up to 3 times its design capacity. We're talking about insulation literally melting off the wires. This is a massive fire risk, and it's all caused by this invisible electrical hum.
So, how in the world do you fight an enemy you can't even see? Well, we've got a secret weapon, harmonic filters. These devices are the heroes of our story. They are engineered for one specific purpose, to hunt down and get rid of this electrical pollution before it can cause any real damage.
Our first hero is the active harmonic filter. And honestly, the best way to think about it is like a pair of noise-canceling headphones. It actively listens to all that electrical noise in real time, and then, in less than a millisecond, it generates the exact opposite mirror image waveform to perfectly cancel it out. All this left behind is the clean power we wanted in the first place.
And our second hero is the passive harmonic filter. Now this one's a little different. It works more like an off-ramp on a highway. It's a much simpler, really rugged circuit that's just tuned to a specific frequency. It gives those annoying harmonic currents an easy way out, a path of least resistance, diverting them safely away from the main system before they can cause a huge traffic jam. Okay, so we've got our 2 heroes, right? One is high-tech and dynamic, the other is simple and super rugged. So let's put them head-to-head and see when you'd actually use each one. So what's really fascinating here is the trade-off. Active filters, they're dynamic. They can adapt as the electrical load changes, which is perfect for a modern office where people are turning computers on and off all day. Passive filters, on the other hand, are best for really steady, predictable loads, like a giant fan in a factory that just runs 24/7. Now, active filters cost more up front, but one single unit can protect an entire electrical panel. Passive filters are cheaper, but you often need to install one for each problem machine.
And this diagram just perfectly shows the two main ways they get installed. So on the left, you see a shunt filter. It connects in parallel to the main circuit. That's our off-ramp we were talking about. It's actively pulling those nasty harmonic currents out of the main flow. Then on the right, you have a series filter. This one's placed directly in line with the circuit, and it acts more like a gatekeeper or a barrier that literally blocks the harmonics from getting through. Shunt filters are way more common for cleaning up a whole system, but a series filter can be absolutely vital for protecting one single super sensitive piece of equipment down the line.
But hold on, this isn't a simple choice. There's a big twist in our story. Because if you try to solve this problem the wrong way, you can make things catastrophically worse.
This right here is the critical question every engineer has to ask, especially when you're dealing with passive filters. If that filter isn't sized perfectly for your specific electrical system, you don't just fail to fix the problem, you risk creating an absolute monster.
And that monster has a name: resonance. This is the stuff of nightmares for electrical engineers. It's what happens when your filter, the thing that was supposed to be the solution, accidentally tunes the entire building's wiring to the exact same frequency as the harmonic noise it's trying to eliminate.
And when resonance happens, the filter becomes an amplifier. Instead of removing the harmonics, it magnifies them hugely. Currents can skyrocket to 10 times their normal levels. You get massive voltage spikes that can puncture the insulation on motors and transformers. We're talking about explosive failures, blown capacitors, total system collapse. This is exactly why you can't just grab a filter off the shelf. It requires really careful engineering to get it right.
So, after all that doom and gloom, let's zoom back out. Why on earth do we go through all this trouble just to fight an invisible electrical hum? Well, because the benefits of having clean power are absolutely massive.
You know, at the end of the day, this isn't just about preventing a disaster. It's about making everything more efficient and more reliable. Cleaning up harmonics makes all your equipment last longer. It can actually save you a serious chunk of change on your energy bill, maybe 5 to 15%. It stops those incredibly frustrating random circuit breaker trips, and it keeps you in line with the power quality standards that the utility company requires. It's just smarter, safer, and cheaper in the long run.
And that really just leaves us with one final thought. As we keep adding more electronics to our lives, more electric vehicles, more solar panels, you name it, all of which are sources of harmonics, our electrical grid is only going to get noisier. So the real challenge moving forward isn't just about generating more power. It's about making sure the power we use is clean enough to keep our electrified world running smoothly. How do we make sure the signal doesn't get completely lost in all that noise?